Hello everyone, welcome back you all in this new video. Here we are going to see the manual approach for the strap foundation design. This complete problem we are going to solve in 5 important steps. In the first step we will see the problem statement along with the brief general discussion about the strap foundation. In the second step we will see how to decide in plan dimension of the foundation as length, width and depth. In the third step we will see the design for the reinforcement along the length and width of your foundation. And in the fourth step we will see the final design of your strap beam which will connect two isolated foundations. And in last step we will see the final schedule and detail in respect of your design results. For better understanding of everything, you have to watch this video till the end. And if you are interested in the field of structural design and you are new on this channel, so we are continuously uploading this kind of videos, so please subscribe this channel and share this video with all of your friends and press the bell icon to get every notification. First of all, try to understand the problem statement. Two columns having the cross section as 240 by 240 and 300 by 300 in mm. They are subjected to the intensity of the load as 300 kN and 500 kN respectively. The center to center distance between these two columns is 4 meter. The bearing capacity of the soil at the proposed land is 100 kN per meter square. We have to design this combined foundation with the strap beam being width of the foundation as 2 meter. The grades of the material you have to use for the concrete as M20 and Fe415, that for the steel. Here we need to understand that what does mean by the strap foundation. So strap foundation will consisting of two isolated foundations as F1 and say F2. Among these two isolated foundation, one will be eccentric foundation and another will be concentric foundation. What does mean by the eccentric foundation, concentric foundation? Eccentric foundation in which the column is going to be positioned not at the center of your footing. It is what somewhere at other location the column is going to be positioned. So that footing we are going to call it as eccentric foundation. And in another way there will be what? Concentric foundation. It means that there is a foundation slab, over that the column is going to be centrally positioned. So we are going to call it as concentric foundation. So if these two foundations are going to be connected by the strap beam, then we are going to call it as strap foundation. So in this problem first we will design these strap footings. First we will design these two foundations. We will find out the dimensions of these two foundations. We will find out the reinforcement in these two foundations along the length, along the width. Thereafter we will go to design this strap beam which is going to connect these two foundations. Now let's start the design. So first of all we need to know how much the load coming from both of the column. So from the first column the load coming as 300 kilonewton and from the other column the load is coming as 500 kilonewton. So if we are going to add these two values, so you will get total load coming from both of the column as 800 kilonewton. Thereafter we need to consider the self weight of the foundation. So to know the self weight of the foundation, we need to know the length of the footing, we need to know the width of the footing, we need to know the depth of the foundation. But without of the design, how you will come to know how much the length is there, how much the width is there, how much the depth is there. So that's why we need to go with the assumption. So what assumption I am going to take here to find out the self weight of the foundation as 10% of the load coming from both of the column. So self weight of the foundation will be as a 10% of load coming from both of the column. It is going to become what? 80 kilonewton. If we are going to add this 800 plus 80, so this is actually the load which is going to be transferred to your subsoil. From foundation to subsoil, the total load is going to be transferred as 880 kilonewton. Now if you want to find out the actual area of the foundation required overall, so that you can do by taking the ratio of the load coming from both of the column including of self weight of the footing, that is what? 880 kilonewton divided by SBC of the soil. How much the SBC of the soil has given? So SBC of the soil has given as 100 kilonewton per meter square. So take the ratio of these two, total load divided by SBC, you will get the total area of the footing required as 8.8 meter square. Very simple it is. Thereafter you know very well, area of footing will equal to length of the footing multiplied by your width of the foundation. The width of the foundation, here it is given that the foundation width should not be less than or more than of 2 meter. Here we have to design the combined foundation with the strap beam being width of the foundation as 2 meter only. you are not allowed to take more than of 2 meter or less than of 2 meter. That's why width is going to be fixed as 2 meter. Now there is a question to find out the length of the foundation. So actually there are two foundations. This is the first foundation, there is another foundation, and for this the column here it is present, for this column here it is present. So actually total area required is this much, width is this much. So for both of the footing I am going to say that the width of the foundation will be what, same. Now area, this length is I am going to call it as L1, this length I am going to call it as L2, because it's the footing first, this is the footing second. Okay, and see, L1 plus L2, it is going to become total length of your foundation. So sum of length of the foundation as L1 plus L2, that will equal to 8.8 total area of your footing divided by final width of your foundation. So it is going to become 4.4 meter square. It is not the meter square, it is the meter. Just correct it, it is in meter. After that, we have to find out the CG of the load. At what point the CG of the load is. See, we are going to design the slab foundation, and to have the uniform pressure distribution under the foundation slab, we need to have the CG of this two load and CG of the area of the footing should coincide at one point. Then only we can ensure that our upward soil pressure will be what? Uniform. So first of all, we would like to find out the CG of the load. So to find out the CG of the load, let's say consider that the center to center distance between the column as 4 meter, that is given in our problem statement. The center to center distance between the two columns is 4 meter. So it is, I am going to call it as center of column C1. This is the center of column C2. C1 column having the load of intensity 300 kilonewton, C2 column having the intensity of the load as 500 kilonewton. Now let's consider that there is a CG of the load somewhere here which is at a distance of x from the center of C1 column, and the same point is at a distance of y from the center of column C2. So take the moment, so it is going to become 300 about this point. If I am going to take the moment, it is going to become 300 multiplied by this x, 300 multiplied by this x, so it is going to become anti-clockwise. If I am going to consider this point about this 500 kilonewton force, so it is going to become positive moment. So it is negative, it is positive. So negative 300 into x is equal to 500. This y value is going to become 4 minus x. This y value is actually what? 4 minus x. If I am going to do, I will get this distance. So that is actually here it is written 500 in multiplication of 4 minus x. So therefore we will get the value of x is equal to 2.5, and y is going to become 4 minus x is 2.5. If you are going to take this difference, you are getting the y value as 1.5 meter. So we are having both the values as x and y as 2.5 and 1.5. Now after knowing the value of x and y, we have to find out the L1 and L2 for both of the footing. For that, we are trying to keep the CG of the load and CG of the footing to be coincided at one point in order to ensure the uniform pressure distribution. Therefore, we are going to equate the moments of superimposed and reactive forces about the center of your column C2. This is your column C2 and this is the center of your column C2. So I am going to take the area of total foundation as area of the footing required. It will be what in multiplication with your y. This is what your y. So this value of the area of footing coming in denominator, and with that will equal to the area of this first footing multiplied by this lever arm from the center of column C2 up to the center of your footing 1. This is the first footing. So how you will come to know this distance? So calculating this distance a little bit, it is important to understand how to do the calculation for this lever arm. So it is very simple. We are having the distance center to center as, so it is LCC is the center to center distance between two column, plus this is what B by 2, B by, this is the B1 by 2. Size of your column is 240. Okay, square size of your column is 240. So half of this, it is B1, plus what does it by this LP1? This is the projection of edge of your first footing from the face of your column. So there is no any edge projection. footing projection, your edge of the footing exactly at the face of your column, hence this value of the projection will become equal to 0. Now we are having the total distance up to the edge of footing, but that is what not required. We actually have to calculate the distance up to the center of your foundation. Okay, so that will become equal to total span that we have calculated as LCC plus LP1 plus B1 by 2 minus half of, this is the L by 2 and this is L by 2. Okay, L1 by 2 and L1 by 2. So if you are going to subtract this L1 by 2 from the total span, you are getting this much distance. So it is what actually calculated by this formula multiplied by second area of this second footing. This is the footing 2 and its area is what 2, but it's L2 by 2. This is what the center, and it passes through the center of your column C2. So its movement is going to become what? 0 for this. That's why A2 multiplied by no distance is there. That's why it is what? 0. If you are going to put all the values here, so what will become? Y is what? 1.5 meter. So I am going to put here as 1.5 meter multiplied by area of first footing. So width is what? Common for both of the foundation as BF, and that is what? 2 meter. So BF multiplied by L1, it is what? L1 multiplied by center to center distance between the two column as 4 plus projection, as I earlier told you, the projection is what? 0. So it is 0 plus size of your column, left hand side of column is what? 240 by 240. So half of that is going to become what? 0.12. 240, half of that 120 in meter, it is going to become 0.12 minus L1 by 2. So actually we have to calculate this L1 value. Okay, so it is going to become 0.5 L1 plus A2 multiplied by 0. This term is going to become 0 divided by area of footing required. So total area of the footing required is going to become width of the foundation. Total length of the footing is what? L1 plus L2. This is the total area of the foundation required. Now after all of that, we are going to solve this equation, and we are getting finally as 1.5 will equal to L1 multiplied by 4.12 minus 0.5 L1 divided by 4.4. If you are going to solve all these values, or if you are going to put everything here, so you will get this value. We are having L1 plus L2 as how much? Let me show you. L1 plus L2 is 4.4 meter, not meter square. It is actually in meter. Okay. So 4.4, and width of the footing, here it is denominator, here it is in numerator. I am going to what? Cancel this. Now what is going to become? This L1 will be there. This total addition 4.12 minus 0.5 L1. This term is going to become 0. So nothing is there. Divide by this L1 plus L2 is 4.4, 1.5. If you are taking this here, it is going to become 6.6, and it is going to become L1 0.5 L1 square minus 4.12 L1. If you are going to solve this quadratic equation, we are getting the value of L1 as 2.177. I am going to round up this value. I am going to take higher value like 2.2 meter. Now here we are knowing the summation of your L1 plus L2 is equal to 4.4 meter. Now here we are getting the value of L1 as 2.2 meter. I just want to do the calculation for L2. So that is going to become 4.4 minus 2.2. So finally you are getting the L2 value again as 2.2 meter. So the value of L1 is 2.2 meter. The value for the L2 is again 2.2 meter. So both of the footing is having the same span as 2.2 meter. Now finally I just want to calculate the upward soil pressure. So the formula for calculating the upward soil pressure is what? The load coming from the column divided by area of the footing. Okay, so here the load coming from both of the column is 800 kilonewton divided by 2 times 2 is means what? The width actually multiplied by this L1 plus L2 is 2.2 plus 2.2, again it is 4.4. So after solving this equation, you are getting the value of 90.91 kilonewton per meter square as a upward soil pressure, and this upward soil pressure we will use for the later design of this combined foundation by this strap beam. But here one question, we have to assume the width of the strap beam, the beam which is going to connect these two foundation through these two columns. Okay, so for that I am going to consider the width of the strap beam as equal to the width of maximum size of the column in transverse direction. So actually this is our longitudinal direction or span of the footing I am going to call. This is the transverse direction. So in this transverse direction, the size of the column is what? Maximum size. This is 240 by 240 and this is 300 by 300. So we are going to consider the maximum size of the column. So the width of the beam is what? This one. So beam is passes through the face of your column. Okay, this is your beam. You need to understand that. Let the width of the strap beam as 300 mm. Thereafter, we want to calculate the projection of the slab beyond the longitudinal face of the beam. Here, actually the beam is present in this direction. So there will be no deformation of your foundation slab in this direction. That's why we are going to do the flexural design in transverse direction only. So I just want to calculate the projection beyond the face of the beam, not from the face of the column. This is my beam. Okay, so from the face of the beam, how much the projection is available? So projection, how you can calculate, that is equal to total width of the foundation 2 minus width of your beam 0.3 divided by 2. So you will get this cantilever projection outside the face of your beam. So I am getting the projection outside the face of the beam as 0.85 meter. Now I just want to calculate the moment. So what is the formula for calculating the moment? This is the upward soil pressure multiplied by the projection square divided by 2c. Suppose this is our beam line and this is what our cantilever portion, that is what 0.85. Okay, so upward soil pressure here it is present. So it is the intensity of 90.91. Okay, upward soil pressure is multiplying with the cantilever projection square of that divided by 2 multiplied by unit width. So we are going to do the calculation along the width of the foundation. So 1 meter strip I am going to consider. This is a 1 meter strip, 1 meter width of the foundation I am going to consider in this direction. So it is going to become what? 1 meter is there, but it is not needed to write the 1 meter because answer will be same. So we are getting the moment as 32.84 kilonewton meter per meter width of the design strip. Thereafter, we are getting the ultimate moment as 49.26 kilonewton meter per meter. Now, I just want to calculate how much the effective depth is required. So, we know the formula mu limiting value is equal to 0.138 FCK BD square. This is the formula to calculate the ultimate moment. So here we are going to use this formula to find out the effective depth. So for effective depth, therefore ultimate moment is how much? 49.26 into 10 raised to 6 in Newton mm divided by 0.138 FCK. Characteristic strength of your concrete is 20. We are making this calculation over 1 meter width of the strip. So it is going to become 1 meter means 1000 mm. So ultimately we are getting the effective depth requirement for the foundation slab as 133.595 mm. So it is what the depth required for the flexure. Thereafter we have to calculate the overall depth. So taking the 12 mm diameter of bar and by considering the 50 mm clear cover. So the formula is going to become what? Effective depth plus clear cover plus half of your diameter of bar. So it is going to become what? 189.595 is the overall depth required for the flexure. Whatever the moment is coming to resist that moment, how much the depth of the foundation is required, it is actually 189.595 mm. Now, if I am going to take this depth, so there may possibility that on later stage, this depth may get fail under the one-way shear or punching shear check. That's why we are going to provide the overall depth of the foundation slab slightly more than that of the requirement. So I am going to take overall depth as 450 mm. Overall depth of both of the foundation I am going to consider as 450 mm. Just come down. How much the effective depth available now? So available effective depth with this 450 mm overall depth, it is going to become 450 minus clear cover minus half of your diameter of bar, that is 6 mm. You are getting the available effective depth of the your foundations as 394 mm. Now this depth of the foundation we will use on later calculation. Here I have to perform the one-way shear check whether our provided foundation depth is safe or not under the one-way shear check. So for that the shear force at a distance of D from the face of the beam. Again, suppose this is your foundation, have a look over this, and there is presence of beam. Here the beam is present. Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program, you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real life project, we will cover the raft foundation. And in the fourth real life project, there will be the coverage of pile and parquet design of basement wall. And at the end of this training program, we will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by experts. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now, more than 1,000 participants have benefited from this training program. Now you are the next. Here the beam is present. Okay. Now, at a distance of D from the face of your beam, I just want to calculate the one-way shear force, which is at a distance of D from the face of your beam, not from the column and not along the span of the foundation. We are going to do the calculation along the width, along the transverse direction. Remember, there is some slightly change from the common practice of the design of your foundation. Okay, so here the shear force at a distance of D from the face of the beam, it is going to become what? 90.91 upward soil pressure multiplied by, this is what, try to understand, this is our foundation and this is your column is present, and now the beam is coming from here like this. This is your beam. Your size of the column is what? 240 by 240, and your beam width is what? It is actually 300 mm. That's why we are having this much gap. Okay, so the shear force at a distance of D from the face of the beam, from the face at a distance of D, this is the one-way shear section. I am going to consider the one-way shear section, which is at a distance of D from the face of your beam. So upward soil pressure, and this total projection is how much? We have earlier calculated as 0.85 meter. This much projection from the face of the beam up to the edge in transverse direction. So 90.91 upward soil pressure multiplied by 0.85 minus this effective depth. So you are getting this remaining span. Actually, we have to do for this remaining span. So for remaining span, we are getting the shear force as 41.455 kilonewton. I just want to calculate the factored value. So we are getting the factored value as 62.182 kilonewton. This is what your ultimate shear force at a distance of D from the face of your column for the one-way shear check. Now, nominal shear. How much the nominal shear is going to be developed at that particular section? So it is going to become 62.182 into 10 raised to 3. The shear force at that point divided by 1 meter width multiplied by effective depth of your foundation. So we are getting the nominal shear at that one-way shear section. We are getting as 0.1578 MPa Newton per mm square. This is the nominal shear. Now I want to see how much the critical capacity is there at that critical section. How much the load carrying capacity or stress carrying capacity at this one-way shear section. I just want to calculate that, and that is we are denoting by tau c, critical capacity. Okay, so to find out this tau c, we need to know the percentage of reinforcement available at this section. So without designing for the reinforcement, you cannot perform the one-way shear check. Unless and until you are not having the reinforcement at that particular section, or unless and until you are not knowing how much the percentage of reinforcement available at that section, you cannot check against the one-way shear. That's why here we need to assume the percentage of reinforcement at that critical section. Till now we have not designed for the reinforcement. Then how you can come to know how much the percentage of reinforcement available there? That's why what we are going to do the consideration. So we are going to consider the minimum percentage of reinforcement is available at that section. In any design, at least you will definitely provide the minimum percentage of reinforcement. What minimum percentage of reinforcement has suggested by your IS 456-2000? In any kind of the foundation slab, minimum percentage of reinforcement should be at any location, at any section, it should be 0.12% of B into D. this much should be there at least. So I am going to consider 0.12% anyhow will be there. If my design is going to be satisfied with this minimum percentage of reinforcement, means it's obvious if I am going to provide the more reinforcement, that will be safe. But if the minimum is there and my design is going to be satisfied with that minimum percentage, so that's a good thing. Okay, so here what we are going to consider, we are going to consider that there is at least 0.12% of reinforcement is available. Till now we have not done the design. Remember, we just go to make the consideration assumption that there is a presence of 0.12% of reinforcement. For that 0.12% of reinforcement, how much critical capacity is there? So you need to look at IS 456-2000 table number 19. Let me show you. Have a look over this table number 19, design shear strength of the concrete tau c. So the percentage of reinforcement is equal to 0.1% or less than of that. And for the M20 grade of concrete, the value of tau c will be 0.28 MPa or Newton per mm square. But here our percentage of reinforcement available we are going to consider as 0.12%. So our 0.12% is less than of 0.15. That's why this value at least we have to consider as 0.28. So that I am going to do here in calculation. The critical capacity is 0.28 MPa Newton per mm square. Now we have to compare tau v and tau c. If you are getting your nominal shear is less than your critical shear, it means that your provided depth of the foundation is safe and okay. But in a situation we are getting your nominal shear more than of your critical shear, in that case there is a problem either with your provided depth of the foundation or provided percentage of reinforcement in the foundation. Both are variables. If you are going to change these two variables, the value of nominal shear is going to what? Change. Your critical capacity is going to change. So here we are getting nominal shear less than your critical shear, hence no shear reinforcement is needed to provide in your foundation slab, right? Thereafter we need to go for finding out the reinforcement, how much the reinforcement actually we have to provide. So area of steel is equal to 0.5 FCK divided by Fy, and then 1 minus square root of 1 minus 4.6 ultimate moment you have to put here FCK over the considered width that we are making for the 1 meter. Effective depth is square multiplied by b into effective depth. Put all the values, respective values for all these parameters in this equation. So you are getting what? 0.5, 20, 415, 1 minus square root of 1 minus 4.6, ultimate moment is 49.26 that we are having. For that we have done the calculation here. Mu ultimate moment is 49.26. So I am going to put here 49.26 into 10 raised to 6 divided by, it is what? 20. Characteristic strain over a 1 meter width multiplied by a 394 square. This is what the effective depth. Again B is 1000, effective depth is 394. We are getting the area of the reinforcement as 353.019. Area of reinforcement required for the flexure. Try to understand whatever the movement is there, in respect of resisting that movement, we have to provide the reinforcement as 353.019. So this is what the design requirement. I am going to call it as design requirement. Now have a look. What is the minimum reinforcement? As I earlier considered that 0.12% is the minimum reinforcement is present there. So area of reinforcement required as minimum 0.12% multiplied by 1000 is the width considered for the calculation. Overall depth is 450 divided by 100 as it is the 0.12%. So we are getting the minimum reinforcement 540 mm square. Just compare, this is the minimum reinforcement requirement MR, and this is the DR, means design requirement. Compare this DR and MR, we are getting the minimum requirement more than that of the your design requirement. That's why what I am going to do, I am going to provide this much reinforcement at least. And with this reinforcement also we have done the one-way shear check. Okay, so you cannot provide the reinforcement less than of this, otherwise we need to revise the one-way shear check, right? So at least you need to provide the minimum, or more than of that if you are going to provide, that's well and good. Okay, so here now providing 12 mm diameter of bar with a unit area of 12 mm diameter of bar as 113 mm square. Now how much the spacing is required? So 113 divided by 540, over the 1 meter width, so 1000, we are getting 209 mm is required spacing. You are not allowed to provide the spacing more than of these. That's why we are going to provide the spacing as 200 mm center to center. Now this is the calculation actually have done along the transverse direction, but that we are going to implement along the longitudinal direction, along the span of the footing also. So overall we are going to provide 12 mm diameter of bar with a spacing of 200 mm center to center in both way or in both the direction. So have a look how we are going to do the placing of the reinforcement. Very simple it is, try to understand. On a later stage we will look at the placing of the reinforcement in detail, but for the general idea I am just showing that how I am going to provide this design reinforcement in the foundation. So here the column is present at the center, here the column is present here. So whatever the calculation we have done till now, it is along the transverse direction, along this direction. Okay, so reinforcement we are getting as 12 mm diameter of bar at a spacing of 200 mm center to center in this direction, and here it is also same. So you may ask a question, why we are not calculating the movement along the length? Because that all stresses along this span were carried by the beam. So we will consider the flexural action for the beam only in this direction. Okay, so here we have done the design along the transverse direction for this foundation slab, and whatever the value we are getting along this transverse direction, that we are going to implement along the length of the foundation. So with same spacing I am going to provide this reinforcement in this direction also, 12 mm diameter of bar at a spacing of 200 mm center to center for this foundation also, for this foundation also. So here it is going to become both way. Now, after knowing the reinforcement required along the length and width of both of the foundation, we have to design this strap beam which is going to connect both of the foundations. So I am going to consider the width of this beam as 300 mm. And now here it is what the pressure distribution under each of the foundation. So the pressure distribution we earlier has calculated as the upward soil pressure distribution as 90.91. But here we have to multiply this upward soil pressure with the width of this foundation. So I just want to calculate this upward soil pressure over the span of this foundation. So it is going to become what, 90.91 multiplied by full width of your foundation. So just focus on the unit as it is kilonewton per meter square. We are going to multiply over the width, that is in meter. So this meter is going to be cancelled. You are getting the upward soil pressure as 181.82 kilonewton per running span of this footing. Now here we have to design this strap beam. So we are going to find out the shear force and bending moment at different important points. And those important points will be: one at the edge of the foundation, second under the column, third at the edge of this foundation, then fourth here we have to do the calculation, and under the column C2 we have to do the calculation for the shear force and bending moment, and finally at the edge of this second footing we have to do the calculation for the shear force and bending moment. So for that the detailed calculation here it is actually given. So shear force at this first point will be what, 0. Shear force at this point under the column C1 is going to become what, upward soil pressure multiplied by this much projection. So we know that the size of your column is 240. If you are going to divide it by 2, so you are getting 120 in mm. If you are going to calculate it in meter, so you are getting 0.12. So you have to multiply this span with the upward soil pressure as 181.82. So you are getting the shear force value as 21.82. that is what the positive value. Thereafter if you are going to come just right of this point, center point, so you have to include this downward force. So here available is what, 21.82 minus 300. So on the right hand side consideration section you are getting the value of the shear force at 278.18. this is in minus sign, so you are getting the value in minus sign as 278.18. now I have to do the calculation at the edge of this foundation. So how much the shear force will be at a distance of 2.2, because we know that span of this foundation as 2.2 meter. So I want to calculate the shear force at this point. So very simple calculation is there. We have already done the calculation up to the center, that is what, 278.18 minus sign. Now remaining portion is only this much. Okay, that is what 2.2 minus 0.12. So you are getting the span as 2.08. You have to multiply this by the upward soil pressure as 181.82. So you are getting the resultant value at the edge of this first foundation as 100 kilonewton. But that force will be continue up to the edge of this second footing. Why? It is because in between of this span there is no any load, no upward soil pressure is there, no downward intensity of the load is there any. That's why the intensity will be what? Constant up to the edge of this foundation. Okay, thereafter we have to do the calculation for the shear force at the center of your column C2. For that we have already the value up to this point, that is what 100 kilonewton, and it is what the positive value. So that I am going to take here as 100 as a positive, plus it is what remaining portion half, this part you have to consider, and it is again 2.2, half of that it is going to become 1.1 meter. Okay, so we have to multiply this 1.1 with your upward soil pressure as a positive because it is upward direction. So 100 plus 181.82 multiplied by 1.1, you are getting the resultant value as 300 kilonewton. That is what? Positive. That's why it is above the line as 300 kilonewton. But it is under the column, so left section we have considered. Now just come to the right side of this center, so you have to include this downward 500 kilonewton force. So same 300 will be there at the same point, minus 500, you are getting the minus value of 200 kilonewton. It is in downside as minus 200. Thereafter we have to do the calculation at the edge, and at the edge you are getting what? Minus 200 plus this remaining portion as 1.1 meter, upward soil pressure 181.82. This is the minus sign, plus this is again upward, so plus 181.82 multiplied by 1.1, you are getting the 0 value. Obviously at the edge you will get the value as 0. So this is our cross check whether we are doing our calculation right or wrong. So at the edge you will definitely get your shear force as 0. So based on this calculation we have to draw the shear force diagram. Now after that, next thing we have to find out the bending moment at some important points, and those important points are again same. One we have to calculate at the edge of the foundation, then we have to calculate under the column C1, then we have to calculate under the column C2, and finally we have to calculate the bending moment at the edge of footing 2. So I am going to do the calculation for the same. So obviously at the edge you will get the bending moment as what? 0. Now when you come to calculate the moment at the center of your column C1, so only this much projection is there, this much cantilever projection you have to consider, and upward soil pressure is what? 181.82 kilonewton meter. So either you can go with this calculation, let me show you. It is going to become 181.82 multiplied by the cantilever projection is what? Beyond the center of the column as 0.12 meter only. This is only 0.12 meter. So 0.12 is square divided by 2 because it is a cantilever projection. So we are getting the bending moment under the column C1 as 1.31 kilonewton meter. It is the positive bending moment. Sagging bending moment it is. Remember. Next, actually I have to calculate the bending moment directly at the edge of this first foundation here. But in between, if you are going to look at your shear force diagram, so here we are getting 0 shear force point. It is the negative value, it is the positive value. So your shear force is going to be change the sign. Here negative and it is positive. And when your shear force is going to change from its sign as from minus to plus or plus to minus, you are getting the 0 shear force point. Here no shear is there, and wherever you are having 0 shear force point, there you will get the maximum bending moment. So I need to calculate at what distance this 0 shear force point is available. Actually we know this much up to the edge, it is what? 2.2 meter, and this is also we know that it is 0.12 meter, but we don't know how much this distance. So we are going to do the calculation based on similarity of the triangle. So based on similarity of triangle, we are getting this span as 1.53 in meter. Now I am going to add 1.53 plus 0.12 to come up to the edge, because this full cantilever span I have to consider. If you are going to add 1.53 plus 0.12, you are getting 1.65. So at this zero shear force point, I want to calculate how much the bending moment is. So it is, I am getting what, 181.82 multiplied by 1.65, this much cantilever projection, 1.65 square divided by 2 minus this is what, sagging clockwise upward soil pressure is there, so it is taking what, clockwise, but there is another loading coming from the upper side, that is what, 300 kilonewton, it is what, anti-clockwise, so it is in minus sign. So I am going to put here as minus 300 1.53. So we are getting the resultant moment as 211.5 kilonewton meter. It is with minus sign, means it is hogging bending moment, it is negative, downside it is. Positive moment we are going to show above the line, negative moment we are going to show below the line, remember. So here we are getting what, 211.5 kilonewton meter. Now finally I want to calculate the bending moment at the edge of this footing. Now full span is going to become how much, it is 2.2 meter, and this upward soil pressure will be, okay, so the same calculation will be here available, 1.81.82 multiplied by 2.2 square divided by 2 minus this 300, under the column downward load is what, 300 kilonewton multiplied by 1.53, you are getting the bending moment at the edge of footing first as 183.99. It is again negative bending moment, means it is, we are showing this value below the line. Now here it is the bending moment under the column C2. Here I am going to do the calculation for the bending moment. So this much projection I am going to consider only. And how much this projection is? So it is basically 2.2, span of your foundation 2.2, half of that is going to become 1.1. So 181.82 multiplied by 1.1 square divided by 2, you are getting the bending moment at this under the column C2. The same calculation here you can find 181.82 multiplied by 1.1 square divided by 2 as 110. It is actually what, positive, because it is sagging bending moment. You are getting the bending moment at above the line. So 110 kilonewton sagging bending moment, positive bending moment you are getting, and finally at the edge of the foundation you are getting the bending moment as 0. So this is the calculation how to know the shear force and bending moment at different points throughout the span of your beam, that is passes through the center of column. After knowing the bending moment along the span of the beam, we have to design this beam for the flexural requirement. So first of all we need to know the what overall depth or effective depth of the beam is required. For that I need to consider the maximum bending moment along the span of the beam. So how much the maximum bending moment here we got along the span of the beam as 211.5. Irrespective of the sign, we don't need to go with plus and minus. Irrespective of the sign consideration, we had to consider the maximum bending moment. So we are getting the maximum bending moment as 211.5 kilonewton meter. So I am going to consider this maximum bending moment as 211.5, and these all values are actually service bending moment. I have to multiply this service bending moment with 1.5 to have the factored bending moment or ultimate bending moment. So we are having the factored bending moment as 317.25 kilonewton meter. It is not the kilonewton per meter, it is actually kilonewton meter bending moment. Now ultimate bending moment formula is what? 0.138 FCK B into D square. So actually we want to calculate how much the effective depth of the beam is required. So the formula is going to become D is equal to square root of mu ultimate moment divided by 0.138 FCK B. This is the formula to calculate the effective depth. Okay, so you have to put the values here as 317.25 into 10 raised to 6 divided by 0.138. FCK is 20 and B is what? Width of your beam you have to consider. And we have considered the width of the beam is what? 300 mm. So effective depth of the beam is required as 618.99. Almost you can say 619 mm is required. Now here I am going to consider, we will provide the 25 mm diameter of bar, and again I am going to consider 30 mm is your clear cover. So to find out overall depth requirement as equal to 618.99, which is effective depth requirement, plus clear cover as 30 mm plus half of your diameter of bar. It is what it is asking to provide the overall depth as 661.49. So I am going to round up this value by the 700 mm. We are going to provide this overall depth as 700 mm. So finally, I just want to know how much the effective depth available. So it is what 700 minus clear cover minus half of your considered diameter of bar. So we are getting actually 657.5 mm. Finally, we are having the effective depth available for the beam as 657.5 mm. Okay. So further, we have to find out the reinforcement required along the span of the beam, along the longitudinal direction of the beam. So how you can calculate the reinforcement? So actually this is what we have to use these moments to find out the how much the area of reinforcement required along the longitudinal direction of the beam or along the span of the beam, main reinforcement. Okay, so first of all, here it is what negative moment, here it is what under the columns they are positive moment. So this is what the negative moments. Okay, and these are the maximum. Negative moments means what? It is the hogging moment. Hogging moment means what? The reinforcement it is needed to provide at the top face of the beam. Suppose this is our beam, and if you are getting the negative moment, it means that designed reinforcements are required at the top face. So for the top face, we are going to find out the how much the reinforcements are required. So design for the longitudinal reinforcement in beam. So first we are going to consider the ultimate moment same 317.25. So for this moment, how much the reinforcements are required? So 0.5 FCK divided by Fy inside bracket 1 minus square root of 1 minus 4.6 mu ultimate moment that you have calculated divided by FCK multiplied by width of the beam multiplied by effective depth of the beam again multiplied by width of the beam and effective depth of the beam. If you are going to put all the values in this equation, so you are getting the value of area of reinforcement required as 1609 mm square. This much area of reinforcement is required to provide for the top face of the beam, not for the bottom. We will discuss for the bottom later. The longitudinal or main tensile reinforcement required at the top face of the beam as 1609 mm square. So here I am going to provide with a 25 mm diameter of bar. So its unit area is what? 490 mm square approximately. So how many number of bars is needed to provide? 1609 divided by 490. So it is going to become 3.28. So I am going to provide overall 4 number of bars on the top face of the beam. Here 4 number of bars we are going to provide. Thereafter main reinforcement at the bottom face under the column C2. Why we are going to do the calculation under the column C2? See, we are having two columns as C1 and C2. But when you have calculated your bending moment under the column C1, we got the value of bending moment as 1.31 kilonewton meter only. And under the column C2, we got the value of bending moment as 110 kilonewton meter. So amongst these two columns, we are going to consider the maximum bending moment column. So here maximum bending moment column is what? Here C2. So we are going to do the calculation under the column C2 and that we are going to consider for full of the span at the bottom face. Whatever the reinforcement required for this movement, we are going to provide that reinforcement for full of the span at the bottom face of the beam. Okay, so I am going to do the calculation designed for the reinforcement at the bottom at column C2. So under the column C2, how much the bending moment we got? 110 kilonewton meter. If you are going to multiply it with 1.5, you are getting the bending moment as 165 kilonewton meter. Now in respect of this bending moment, same formula you have to use with same width of the beam, with same effective depth of the beam, but with this change the bending moment as 165 into 10 raised to 6. So with all of this calculation, you are getting the area of reinforcement required at the bottom face under the column C2 as 755.43 mm square. Now here, as per IS 456-2000, it is suggested to provide minimum area of reinforcement for the beam as 0.85 multiplied by width. It is coming on this side. So it is 300 width multiplied by either you can consider effective depth or overall depth. Both are okay. Okay, not much great difference you are getting. So here it is what given effective depth, but instead of that I am going to consider overall depth. Okay, and if you are considering effective depth, that also be right. Both you can consider. No need to worry about. So here 0.85 multiplied by 300 multiplied by overall depth as 700 divided by 415. So it is asking to provide a minimum reinforcement in your beam at any section as 430.12 mm square. But demand is what? 755.43. So in comparison of these two, minimum And design requirement, we have to provide the design requirement as 755.43 because it is the greater one. So I am going to provide this much area of reinforcement, and for that here I am going to provide a 16 mm diameter of bar, not 12, 16 mm diameter of bar, and unit area of this 16 mm diameter of bar is what, 201.06. So number of bars required at the bottom face of the beam as 755.43 divided by 201.06 unit area. You are getting the number of bars required as 3.75. Again I am going to provide even number as round up as 4 number of bars at the bottom face. Okay. So provided area of reinforcement is going to become 4 times 201.06, 804, and required area of reinforcement was this much. So we are going to provide little bit more area of reinforcement beyond of your required area of reinforcement, means we are on safe side. So finally we have designed our beam. At the top face we need to provide the longitudinal or tensile reinforcement or flexural reinforcement. We are going to provide at the top face as 4 number of bars of dia 25 mm, and at the bottom face the 4 number of bars we are going to provide with a dia of 16 mm diameter of bar. So that is what the design for the flexure for this beam, which is going to connect these two foundations, and this beam we are going to call it as what, strap beam. Now after the complete flexural design of the beam, we have to design the beam for the shear. For that we have to consider the critical section at a distance of d from the interior face of the column C1. So have a look over the figure. You can understand that here we have to consider the critical section for shear. So here I am going to consider the critical section at a distance of d from the face of the column C1. This is what the critical section. Here we have to calculate how much the shear force is going to be developed, and then how much the nominal shear stress is going to be developed at this critical section. And we are going to compare this nominal shear with the critical capacity of this section to carry the stresses. If we are getting the nominal shear less than of your critical capacity, then we are going to say that for the beam it is not needed to design the shear reinforcement. But in a situation where we are getting the nominal shear more than of your critical shear, in that situation we need to design the beam for the shear. We need to provide the shear reinforcement. So very first thing, we need to calculate how much the shear force is going to be developed at a distance of d from the face of the column. So for that the distance, total distance, how much the total distance is becoming up to this section. So it is going to become what, this is what your d, effective depth of your beam, and it is what, 0.24 size of your column, and effective depth of your beam is what, 657.5. this is your effective depth of the beam, and side of the column is what, 240. If you are going to add these two, it is going to become 0.24 in meter plus 0.6575, it is in meter. So this is what the complete span where we are going to consider the critical section, where we have to calculate the shear force or nominal shear stress. So the same calculation here it is given. Have a look over this equation. So it is what, the same distance, 0.6575 plus 0.24, and it is the upward soil pressure. By considering the full width of the foundation, so we are getting the value as 181.82. have a look over the figure again so you can understand. Here 181.82 by considering the full width of the foundation. So we have to multiply this with the span. So it is what, we are coming up to this point. Now here for this span, there is the upward reactions, upward soil pressure is there, which is going to create the shear force at this point. But another load is also there which is coming from top to down, it is 300 kilonewton. This also we have to consider. So that I am going to write here in equation, 181.82 multiplied by the full span minus 300. So we are getting the shear force value as 136.82 kilonewton. So here minus sign, it is showing what, downward direction, but irrespective of the sign consideration, we just have to focus on the value. So it is what, the service value, I am going to multiply it by the 1.5. So we are getting the shear force as 205.23 kilonewton as ultimate shear force or factored shear force. Now nominal shear stress, the shear force divided by size of your beam. So 300 is the width and effective depth is 657.5. So you are getting the nominal shear at that critical section is 1.04 MPa Newton per mm square. As well as I just want to know how much the percentage of reinforcement available. So total percentage of reinforcement available is how much? We have provided the 4 bars of 25 mm dia. Have a look over these. We have provided the 4 bars of 25 mm dia at the top face of the beam. Okay, 4 bars of 25 mm dia having the unit area as 490. So here 1 bar having the area 490, we have to multiply it by 4. So we will get the total area of the reinforcement provided. Divided by section size of the beam, 300 multiplied by effective depth. So we are getting the percentage of reinforcement available as 0.994. This much percentage of reinforcement is there. And what grade of concrete is? So our grade of concrete is what? M20, and percentage of reinforcement available is what? 0.994. So based on these two values, we have to find out the critical capacity of the beam section. So we have to refer the IS 456-2000, clause number 40.2.1. Page number 73, table number 19 will tell you how much the shear capacity or critical capacity of that particular section. So have a look over your IS 456. In IS 456, here you can find in table number 19 for the different range of available percentage of reinforcement based on different grades of the concrete respective critical capacity of the section. So here our grade is what? M20. So we have to follow this column M20, and our percentage of reinforcement available is what? 0.99 something is there. So it is coming in between 0.75 and 1. So we have to do the linear interpolation. So for 0.75 the value is 0.56, and for 1% of the reinforcement the value of the tau c will be what? 0.62. Okay, so that I am going to write here in your calculation. For 0.75, 0.56, for 1.62, we have to calculate the value for 0.994. So if you are going to do the linear interpolation, you are getting the tau c value as 0.62 MPa. Now here what we have to compare the nominal shear and critical shear. So nominal shear is what? 1.04 and critical shear is 0.62. So whatever the action you are going to impose over your beam section, it is more than that of the capacity of the section. It means that we need to design the beam for the shear. So basic concept is what? The actual shear capacity of any section will equal to shear resisting by your reinforcement or shear reinforcement plus shear resisted by your concrete. So we have seen that the action is what? More than of the capacity. So we want to know how much the reinforcement we have to provide to resist the shear force. So VUS shear, which is to be resisted by the shear reinforcement, will equal to ultimate load which is going to act minus the capacity of your concrete VUC. So we will get the shear force that is to be resisted by your shear reinforcement. So how much your VU? So VU is what? 205.23 minus VUC is what? Tau c B into D. This is the formula of shear resisting capacity of your beam section. So we are getting what? 0.62 multiplied by width is 300, depth is what? 567.5. So resultant shear force we are getting as 82.935 kilonewton. For this much shear force, we have to provide the shear reinforcement. So again you have to look at IS 456-2000 to find out the shear reinforcement spacing. So have a look over the IS 456 at the same page here for the vertical stirrups. So here I am planning to provide the 2-legged 8 mm diameter of bar I would like to provide. So if suppose 2-legged vertical stirrups I am going to provide. So actually the shear force is coming from this side. So to resist this shear force, 2 legs are available. So one leg is of 8 mm dia. This is also 8 mm dia. Okay, this complete ring is of 8 mm dia. So one leg plus second leg. So 8 mm dia having the unit area as 50.26. So 2 legs are there. If you are going to multiply it by 2, so we are getting what? 100 mm square. So it is actually 100 mm square. Go back to your calculation and have a look. We are going to provide 8 mm 2-legged vertical stirrup. Area of one stirrup with 2 legs. It is going to become 100 mm square approximately. Now the formula here it is given. Have a look. 0.8587 Fy yield strength of your reinforcement and 2-legged vertical stirrup if you are going to provide. So area of that effective depth divided by spacing of the shear reinforcement. So actually we want to calculate the spacing. So take it on this side, take it on this side. Okay. So we are getting the final formula here. It is given as 0.87415 100 mm square effective depth divided by how much the shear force to be resisted by the shear reinforcement, that is actually I am going to write here. So we are getting the spacing to be provided for the shear reinforcement as 286.24 mm. Then how much the minimum shear reinforcement you need to provide? For that, here it is given 0.87 Fy, that is also given in your IS 456 minimum shear reinforcement. Let me show you. In this same only you can find how much the minimum shear reinforcement you have to provide. So minimum shear reinforcement will be at 0.87 Fy, ASB divided by 0.4 into B, it is giving the value of 300 mm. Now compare these two, a design requirement and this is what the minimum requirement. These two you have to see, and among these two values you have to consider the minimum one. So 286 is what the limit beyond which means more than of that you cannot provide. Beyond of 286.24 mm you are not allowed to provide. This is what the design requirement. You are not allowed to provide more than of these. Lower than of these will be okay. So here I am going to provide for the safer side as 8 mm diameter of bar at a spacing of 250 mm center to center. Under the column C1, see it is I am going to highlight under the column C1. Now in the same way we have to do the calculation for the shear design for the beam under the column C2. So here I am going to consider the critical section at a distance of D from the interior face of the column C2. Have a look over the figure. So from the interior face of the column C2 we are going to consider the critical section at a distance of D. Okay, so this is what the D. So total span from the edge of the foundation, how much it is that I want to know. So this is actually what 1.1. The size of the column is what 300 by 300. So half of that it is going to become 0.15. And then this remaining effective depth span is what 0.6575. This much is the effective depth of the beam. So we have to consider the critical section at a distance of D from the face of your column C2. So this is going to become complete span. Now the upward soil pressure is what 181.82 kilonewton per meter. We have to multiply with this by considering the full width. Okay. So here it is going to become this upward soil pressure multiplied by this span. And one another load is there what downward as 500 kilonewton, that also we have to consider. So with all of this consideration we are having the equation as 181.82 kilonewton per meter multiplied by full span 1.1 plus 0.15 plus 0.6575 minus 500. So resultant value of the shear force you are getting as 153.18 kilonewton. So it is having the minus sign means downward direction. We don't need to focus the sign, we just have to focus on the value. So ultimate value of the shear force we are getting as 229.77 kilonewton. Now nominal shear, very simple formula, the shear force divided by section size of your beam, 300 multiplied by effective depth, you are getting the nominal shear as 1.165 MPa, Newton per mm square. Now available percentage of reinforcement same as that of the previous one, 0.994% of reinforcement is there. In respect of your percentage of reinforcement available and grade of your concrete as M20, we are getting the value of critical shear as 0.62 in similar way of the last case. Now here we have to compare your nominal shear and critical shear. So we are having the nominal shear is more than of your critical shear, hence that we need to do for the design of the shear reinforcement. For that I need to know how much the shear force is needed to be resisted by your shear reinforcement. So VUS will equal to VU minus VUC, shear capacity of your concrete. So here actual shear force is going to be developed at the considered section is 229.77, here it is available, minus critical capacity of your section. So 0.62 multiplied by 300 multiplied by effective depth. So ultimately we are getting the resultant shear force which is to be resisted by your shear reinforcement is 107.48 kilonewton. Now here again I would like to provide as 8 mm diameter of bar, 2-legged vertical stirrup. So area of the reinforcement approximately going to become as 100 mm square. For that how much the spacing is required? So the for spacing calculation 0.87 yield strength of your steel multiplied by area of one stirrup 100 mm square multiplied by effective depth divided by shear force. So actually your shear force is how much? 107.48. Here we have to correct it, 107.48. This is the value. So with the calculation we are getting the spacing requirement as 220.86 mm. This much spacing you are allowed to provide. Beyond of this spacing, you are not allowed to provide the shear reinforcement. This is the last limit. Okay. And for the minimum reinforcement, 0.87 Fy ASV divided by 0.4 into width of your beam. So we are getting the value as 0.87 multiplied by yield strength of your reinforcement as 415 multiplied by area of two-legged vertical stirrup as 100 divided by 0.4 into 300. We are getting the value as 300 mm. So in comparison of these two, you have to consider the minimum one. So what minimum one we are getting? 220. Okay, so 220 you cannot provide, you have to round up this value. So we are going to provide the spacing as 200 mm center to center. So finally we are going to provide two-legged 8 mm diameter of bar vertical stirrup at a spacing of 200 mm center to center under column C2. So this is what the final calculation for the shear design of your beam only. So we have completed the design of your foundation slabs, we have completed the design of your beams also. After the completion of the design, we have to prepare the detail in respect of your design result. So first of all, we are going to see how much the reinforcement required. So first of all, we are going to see how much the reinforcement we have decided to provide for both of the foundation. So have a look over the design results. So for the foundation design, we have decided that we will provide 12 mm diameter of bar with a spacing of 200 mm center to center in both of the direction for both of the foundation. So in this sectional elevation details, here it is showing that for the foundation first, the reinforcement will be what 12 mm diameter of bar at a spacing of 200 mm center to center in both of the direction. Likewise for the foundation 2, we have to provide the reinforcement as 12 mm diameter of bar at a spacing of 200 mm center to center in both of the direction. In plan detailing, you have to do in the same way that it is showing that reinforcement along the length of the foundation, reinforcement along the width of the foundation will be as 12 mm diameter of bar at a spacing of 200 mm center to center for the footing first and for the footing 2. So in plan detailing and sectional elevation detailing, both are actually present here. In this way you have to detail. But one more thing is there, that is what the strap beam which is going to connect both of the foundation. So we have to prepare the detail of the beam also in respect of your design result. So in the design, we have decided to provide the reinforcement for the beam at its top face as 4 bars of 25 mm dia. So that I have presented here for the beam at the top face 4 bars of 25 mm dia is there, and at the bottom face there are 4 bars of 16 mm dia. You can see in your design result as for the bottom face 4 bars of 16 mm dia for the beam. So here the same thing is actually present, 4 bars of 16 mm dia. And what about the shear design? So under the column C1 and for rest of the portion, the reinforcement we have to provide as two-legged vertical stirrup of 8 mm dia at a spacing of 250 mm center to center. Look at your design calculation. Under the column C1, we have to provide 8 mm dia at a spacing of 250 mm center to center. But for the column number C2, we have to provide 8 mm dia as vertical stirrup two-legged at a spacing of 200 mm center to center. Look at this. Here it is present 8 mm dia at a spacing of 200 mm center to center. And is what sectional elevation of especially for the beam as width of 300 mm, as overall depth as 700 mm, and the reinforcement at the top as 4 bars of 25 mm dia and at the bottom 4 bars of 16 mm dia. So in this way overall you have to prepare the detail in sectional elevation, you have to prepare the detail in plan, and you have to prepare the detail especially for the strap beam. So this is actually the complete design for your combined foundation with the strap beam, and this foundation we are going to call it as strap foundation. Hope that you all understood this complete problem. If you are having any doubt and problem, you can write in the comment box. Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program, you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real life project, we will cover the raft foundation. And in the fourth real life project, there will be the coverage of pile and pile cap design of basement wall, and at the end of this training program you will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by experts Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next.